Well, we'll see how this works. Cox hasn't given back my internet connection, but I'm running off my cell phone. I'm got a hotspot going on, so let's see what happens here. Let me know if I start going in and out, because like I said, I'm running off my cell phone. It's a hotspot, so it'll be a first time here. Okay, so as we were, let me see if we get past this slide here. So as basically, again, the overall bond length was actually smaller, less than the combined bond of the particular atoms, okay? And that's because they overlap. That diagram on the far right, you can see where there's overlap of the electrons to form this bond. Okay? So one thing about bond forming, and that's what chemistry is all about. We're basically just creating bonds or we're breaking bonds. Okay. And so for those of you who just came in, I just rehashed what I'm trying to get past that one slide 13, that the sum of the bond length, the new bond length of the compound made is much less than the sum of the radius of each individual atom. Okay. All right. Pretty self-explanatory. Now, with respect to bond energy, and the making and breaking of bonds is what chemistry is about. We're making bonds and breaking bonds someplace to make compounds. Something's happening. And it takes energy to do this, either to break or form a bond. So it's required either way. So when we break bonds, it requires energy. It makes sense. So if I got to break something, I need energy to break that thing. Okay. So when we talk about, with respect to energy, energy is an absorbent. And we call that an endothermic reaction. And you might be familiar with this example. And if you go to the pharmacy, for example, and purchase a co-pack, it's a co-pack, low package plastic container bag that you take and you smack it. And when you smack it, it gets cold. You know, you got a sore muscle or something, you put ice on it and you don't have ice, so you go get a cold pack. And by breaking that package inside the package, it allows a liquid to come in. Most of the time it's water. That could be something else. And during the formation of whatever's happening there, okay, it gets cold. And we call that endothermic. Okay, because what's happening, bonds are being broken. And to break bonds, it takes energy away from the environment, results in it feeling cold. Okay. And we write this in this reaction. Here's a typical chemical reaction. We have HCl plus heat. And that arrow tells you we got something happening here, be it a physical or chemical process, something's happening. So to the left of the arrow are the reactants, and to the right of the arrow are the products. So in this case, in this type where we're breaking a bond, we're taking hydrochloric hydrogen chloride, and we're breaking that hydrogen chloride bond. And that requires energy in the form of heat to form the hydrogen atom and the chlorine atom. And it gets, this reaction will be cold, and we call that endothermic. Okay. When we form bonds that come together, it releases energy. Energy is given up. And that is exothermic. One way to remember, X for exit, energy exits the building, so to speak. And so that thing gets hot. Again, you go to the pharmacy, buy yourself a hot package. You get it, smack it, chemicals in there get warm, okay? Giving off heat, because what's happening in that process is you're forming something, a bond, and heat and energy is released, okay? So in this case, energy is a product and it is produced, and so we write it as follows. And this is the opposite of the reaction we just showed you, in which if I take the hydrogen atom and I take the fluorine atom, not the, we know it's diatomic, but that reaction that brings them together to form the compound hydrochloric hydrogen chloride as a gas, it will give off heat and becomes exothermic. Okay. And guess what? The same amount of heat required to break that bond, it's the same amount of heat as it is to form it. So if it took 100 units of energy to break the bond, it's going to give off 100 units of energy to form the bond. Conservation of energy. Okay. Now here's some true and false true and false question about this particular species, H2S. Okay, hydrogen sulfide, another foul smelling gas. All right, so first thing we notice is that it's hydrogen and sulfide. So we have an covalent compound. Being a covalent compound means that the bonds are shared, right? If hydrogen was replaced with sodium, for example, which there is a compound such that, compared to NaQS, this is sodium sulfide. Sodium sulfide is ionic compound, okay? Compared to H2S, which is two nonmetals, which is a covalent compound. The sodium sulfide is a ionic compound. So with respect to H2S is true. This is a true statement. Being covalent, electrons are shared, okay? The bond between the hydrogen and the sulfur is ionic, and that's a false statement. Okay? Because hydrogen is not a metal and sulfur is not a metal. So that is a false statement. Now we arbitrarily put H2S, but this could be any combination of any other nonmetals, okay? So that's important that you recognize who's a metal and who is a nonmetal. We won't be doing a lot of, literally no work in semi-metals. It's either going to be a metal, non-metal combination or a metal-metal combination. The hydrogen sulfur bond length is less than the sum of the two atomic radii, which is a true statement. Why? Because it's covalent, just like the previous slide, we saw an area of overlap between the electrons, okay? And breaking the HS bond releases energy, and it's false. Remember, breaking the bond requires energy. Okay, so it's not, that's a false statement. Let me clear this up. All right, so which brings us to the beginnings of this Lewis dot structure, which we started in the beginning of the hour asking questions about, okay? Now, Lewis dot structure deals only with the valence electrons. That's important to recognize too. All the action is on the valence shell, okay? And the outermost shell. And that's where reactions occur. They're not going to occur in the core or the inner electrons because they're full. And, you know, in the outer shell, either need electrons or they want to get rid of them. Okay, that's where all the action's at. So we need to identify the number of valence electrons, and one way to describe them is to draw these valence Lewis dot structures for the atoms. We were going to learn how to do Lewis dot structures for compounds, but right now it's simply atoms. And again, this only applies to the A elements. Okay, Roman numeral 1 through 8A. The group number tells us the number of valence electrons, okay? And we start putting a dot to represent those number of valence electrons. And you simply put dots around the atom with the number of valence electrons it has. And, you know, think of that symbol as a square, and we put a dot on each side of that square, and we go around the square until we fill it up. For example, let me demonstrate that by, let's say we have some hypothetical element. I just denote by A. So think of it as a square. And I'm going to put this dotted line that represents the square. And maybe A has one valence electron. So we put one valence electron on the outside. Maybe it's got two valence electrons. So we go to the next side. Doesn't make a difference which side, but not the side we already put one in, but the other free side. I go right side, I go left side, makes no difference. Clockwise, counterclockwise. For the third electron, we go around to the next side. So that's 3. And for the fourth, we go to the far left, the one that's not complete. Now we start filling up the sides with remembering 2 electrons per side. So maybe it's got 5 valence electrons. So we keep going around the horn, so to speak, and put it there. That's 5. Now, whether I put it on top, left, right, bottom makes no difference, okay? The next one, down now in this scenario, the top of the block is full. We can only put 2 electrons there. Remember, 2 electrons per orbit, if you will. All right, so the next electron will go to this side, for example, or to any of the empty sides, whatever you choose. And finally, keep going around the horn. We got 7 valence electrons. That denotes a group 7. And then finally, we get all the way around to the 8 electrons. That denotes a noble gas configuration, okay? But the key thing to remember is to go around the horn. So you wouldn't see, it would be incorrect to write 2 electrons like this side by side. So that implies that you put them in the same orbit, but in same orbital, but they got to go in separate orbits, fill those orbits up all the way around the horn until we get done. And we get the 8. Okay, so that's all that part's telling you. Keep them separate until you start filling it up with the maximum of 2 per side. All right, so let's do the Lewis dot structures for K, which is potassium, oxygen, okay, silicon, magnesium, and iodine. And so, well, here we go. We take potassium, we write down potassium, and we look for it on the periodic table. It is in groups 1A, and guess what? 1 electron. Now, whether I put it there or I put it on the other side makes no difference as long as you got 1 on 1 dot. How about oxygen? What group is oxygen in? Okay. Yes, it's in group 6. So to denote the Lewis dot structure, you go 1, 2, 3, 4, 5, and 6. Now I went clockwise. You want to go counterclockwise? That's fine. You want to start here in the bottom? That's fine. But 1, 2, 3, 4, 5, 6. That is correct. Just as the first one I wrote. Okay. And silicon, we go to silicon. It is in group 4, just like carbon. And so its Lewis dot structure would be as follows. Magnesium is in group 2. And so we got 1 and 2. Okay. Be it like that, or, be it this direction, that's fine. Be it any combination thereof, as long as they're not on the same side. Okay. Any of those would be correct. And then, of course, the final one, we got iodine with 7. So go 1, 2, 3, 4, 5, 6, and 7. Okay. And so that's drawing the Lewis structures. Let me show you the one that's a little bit cleaner picture than mine. All right, so there you go. This Lewis dot structure, again, only applies to the 8 elements, group 1 through 8A. We can't predict the other ones without having more information. We put it that way. And the reason we can is, again, for example, we know that everyone in group 1 will have a +1 charge when they become ions. Copper can have a +1, but it also can have a +2. Okay. Iron can have a +3, but it also could have a +2, or it can also have a +3 charge. Varies from conditions. So, but we can't predict it, but we can calculate it. Okay. You might say, well, what are you talking about, Fred? Well, let me show you what I'm talking about. Take what you learn right now and we're going to extrapolate. Okay. Now, let's take a look of this formula here. We're not going to worry too much about the name of it right now, but I'm going to go and give it to you. And it's iron 3, Roman numeral 3 chloride. And there's a reason for the Roman numeral, which we're going to learn the part. That's the name for it for right now. Now, the question is this: what is the charge on the iron? Knowing the following two things. Okay. Remember when we talked about putting them together earlier, when we had those few examples, I said I had to put enough negatives and positives to equal 0. Okay. And so that should tell you that the number of charges on the chloride should equal the number of charges on the iron to cancel out, right? So it has to, the overall charge should equal 0. Okay. So another way to say that is to say the number of cations plus the number of anions must equal 0. Okay, remember that. Now, this is called iron. Excuse me, that's iron. I'm going to look at iron. Iron, that's the letter N. Iron 3 chloride. Okay. What does that tell you about the charge on the Cl? Chloride. I like the shirt. I just saw that. Yeah, I got some crazy shirts around. Chloride. What does that tell you about the charge of the chloride? It's an anion. That's correct. But what does it tell you? It's charged though. What group is it in? It's in group 7, right? It's going to have a -1. That's good. Okay, so we're going to take that information and extend. Now, how many chlorides do I have? What does that subscript tell you? 3, right? So what is my total negative charge for the chlorides? -3. You got it. And that's equal to 0. So what is it I don't know? The iron. So Fe -3 equals 0. What do you think the iron charge is? +2. Exactly. Because the number of cations, I should say cation charge on both ends must equal, sorry, the resolution of my pen is not the best, but it's number of cation charge plus the number of anion charge must equal 0. The number of anion charge is -3. That means the iron has to be a +3. Okay. And therefore, that is why we give it a Roman numeral 3, because this is one of the metals, not part of the Sweet 16 I gave you before, that we know 100% of the time what the charge is. What do you think with that information? What do you think the charge is on this example? This is also iron chloride, but which one? Iron 2, exactly. So this would be iron, Roman numeral 2, chloride. Both of these compounds have the base name of iron chloride. The difference is the oxidation number or the charge on the iron. The top one is a +2, the bottom one's a +3. Wholly different compounds, wholly different properties. And the only difference between the two is the loss of one crazy electron. Okay. One literally is like plucking your hair off and you become Dr. Jekyll or Mr. Hyde, one of the two. All right. That is what drove me into, got me interested in chemistry, is the power of those electrons. What that, remember we gave it an AMU of 0 because the mass is essentially nothing compared to the proton and neutron, but yet the power it has is mind-boggling. All right, so kind of introduced that a little bit early, but that's okay. When it comes to you, it won't be so, hopefully, so foreign. All right, so we left here Lewis dot structures of atoms, okay? Only good for groups 1A through 8A. Can't predict that unless you know from around. You can't even use it for the other elements. So it brings us to Lewis dot structures for actual compounds, okay? And how they work, because we're going to take this and we're going to also take something else, the shapes table, okay? I need to pull that up here because I had to shut down and I lost my shapes table. Give me a second. Let's see later. Okay. If you've not downloaded this, you really need to, because you know we're going to give you a formula. You're going to be given a formula, and then based on the number of based on the number of valence electrons that every atom brings to the structure, we're going to put a structure together, and then we're going to come up with a general formula, which is denoted by the letters A, B, and E. Again, a general formula where A, notice that first column there in your product table, A is the central atom, okay? A represents the central atom, and let me denote it here. A is equal to the central atom. Remember, I mentioned to you in a structure, chemical formula, we have an atom that is the central atom, normally is the first one written. And then what follows is whatever's bonded around the central atom. And so that's what B represents, is whatever is bonded to the central atom. And it could be the same atoms or it could be different. Makes no difference. Whatever is bonded to the central atom. Okay. And we denote a subscript. And I'm going to just call it X. X could be 1, it could be 2, it could be 3, it could be 4. That's the maximum, 4. So there could be 4 things bonded around the central atom. It could be 2 things and 3 things and so forth. And then E, the letter E represents a pair of non-bonding electrons. Okay, earlier I talked about a pair of electrons that actually form a bond, but there are a pair of electrons that do not form a bond and just simply sit on the central atom. And those are that is denoted by the letter E, and also that also has a subscript X, which can be anywhere from the B. This could be X, can be from 1 to 4 for B, and X for E, technically 1 to 2. Okay, 1 to 2. There are some other things here, but we're 1 to 2. And you can see the image here in the second column of the shapes table. You got 2 dots. Those are lone pair of electrons on the central atom, okay? So once we figure out from the valence electrons a particular structure which gives us A, B, and E, we come to the shapes table and we look up in the first column, what is the general formula for that particular compound based on the valence electrons. So if it turns out to be AB4, for example, which is the most common one, where you have A as the central atom and you have B, 4 things bonded around central atom, guess what? Its molecular geometry is called tetrahedral. And here we have the central atom, and then bonded around it are the 4 moieties, whatever they may be, all distributed. That image is trying to show you a 3-dimensional model, because remember, we live in a 3-dimensional world, okay? And that particular shape, remember that that line represents a bond. And so we got 4 bonds here, which have electrons and they have negative charge. And so they want to repel each other such that they are further, as far away from each other as possible. And when they do that, that's the structure that you end up with, tetrahedral, okay? And there's a bond angle associated with that, 109.5. That is the bond angle between the central atom and any of the 2 moieties bonded in the central atom. Okay, so let me rehash. For the Lewis dot structures for compounds, we're going to calculate the number of valence electrons available to make that structure. We're going to denote who's the central atom. Then, knowing who the central atom is, we know who to bond around the central atom. And then we start connecting the dots, if you will, with bonds, keeping track of the total number of valence electrons that we have. Keeping in mind that we want to position them and put them together such that the octet is fulfilled around all of them. This is what I mean. If I have, let's say, water, we're going to do water. We're going to come up with this structure like this. That line represents 2 electrons, right? And we're going to know that on the oxygen, they're going to be 4 dots. So each dot represents a electron. So I got a pair here. And I got a pair here. Now, around the oxygen, there is a total of 8 electrons. 4 of them are not bonded, but 4 of them are bonded. So guess what? The octet has been fulfilled for oxygen in this mode. For hydrogen, these 2 right here, they're being shared between the oxygen and the hydrogen. Therefore, they count both for the hydrogen and the oxygen because they're being shared. And so the number of electrons around hydrogen are 2, which, remember, the hydrogen rule is a duet. And so the octet has been fulfilled and the duet has been fulfilled here. Okay, does that make sense here at this point? Maybe not, but once we do some examples, we'll see how that comes about. All right, I got about a minute left. Well, with a minute left, why don't I just stop it here on this slide, which would be 17. Okay, we'll continue. I'm pretty sure I'm going to have to move this exam also because we have 45 slides, actually 44. And this does take a little more time of explanation than the other slides. But yes, the test on Thursday will be on chapters, 4, 5, and 6. Okay. 4, 5, and 6. That's it. You know, you have 5. The 5 exams you have are broken up into chapters. So, and those
I have a question.
Sure.
I like I just finished lab 6. I haven't turned it in yet because I'm scared I'm going to turn it in and I'm going to get like 20 points out of 100. How can I use a tutor every week, like 2 to 4 times a week. Like I'm always there to help double check answers and stuff. But is there another way that like you might be able to help make sure that like we're on the right path that way?
Yeah,
If
if you have a question about any other questions, shoot me an email. I'll look
okay,
at the
I feel like
question.
I'm always emailing you.
Don't worry. Don't you guys don't feel like email me as much as you need to. And this is your class. You paid money to learn this class, so you're the customer. So you if it takes 100 emails, it takes 100 emails. Okay, as long as you
Okay.
and what you need. And yeah, email me through Canvas because I get that on my phone and I can answer fairly quickly. And if you use my EDU email, I rarely check that because it's loaded with email from GCC and SCC. A lot of it's junk mail, and you might get lost in there. But with Canvas, I get nothing but Canvas. That's it. Period. I know that's you guys. So yeah,
Okay. And for the lab material,
yes.
I feel like I'm kind of getting like, so what are my resources to find like all of the information? Like I've kind of tried using the textbook online and I actually bought a chemistry book. I'm not sure if it's exactly the right one, but it
Okay.
was supposed to be for another Chem 130 class, like another semester that I just decided I didn't want to take.
Okay.
But I just kind of find myself having to like really dig to find
Right.
answers.
Um, that is the tough part
The
about
point.
yeah, that is a tough part about summer school is that we crunch in 16 weeks and into 8 weeks. And so, for example, the lab normally is one lab a week, and our lectures are like all day Friday for SEC. So we got like 3 hours, like it's all one day. And so I can spend a little time with the lab because it is by definition on your time. And we try to design it so everything you need with respect to the lab is given to you either as in the form of a video or in the form of some PDF file. Okay, and so if there is a question about it, and that's why we leave it open, is you shoot me an email and then we can set up a Zoom or I can answer the question through an email. But normally, if we were face to face, those questions could be answered obviously much easier. Being online just puts a different challenge with respect to the lab part.
Right.
Yeah, I understand it's not the answer you
Okay.
would hope,
No, it's
but
okay. No, it's okay.
yeah,
I think I've kind of navigated just fine. I just wanted
yeah.
to, I don't know. I
If
guess I
there,
just want validation.
yeah, oh, well, that's fine. If you, and that's good because that's the disadvantage of on your time scenario is you're like first time you see it, you're like, wow, am I going the right? I get it, I understand, and that's why I tell you guys if there is a question, feel free to email me 10 times a day if you want. It doesn't make
Right.
a
Because
difference.
I feel like I kind of completed lab 6, but then what you just went over today kind of went over like aspects of that lab. So it's a little helpful, but
Okay,
you
but
know what I mean?
yeah, and you're welcome, if you think you base, because normally we would have covered this before the lab. Okay, we try to correlate the two. So we covered, in other words, I covered this in the lecture. And so when you are in the lab is not as foreign. But again, being in the summer, everything is crunched up. So we haven't covered it yet, unfortunately, because of the time span. And I wish I could we could open the lab up right now, but no, we can't, because the lab part for chemistry is really needs to be done a face to face, and unfortunately we can't at this time.
No
So
worries.
yeah, so we're trying to find the best we can scenario. So if there is a problem, just shoot me an email, and if it comes where we lead to, we can set up a Zoom with whomever needs to, and we can talk about whatever subject matter. I don't have a problem with moving the labs over. I had to, give specific times, but if there's a problem with one particular lab because we haven't done it, I can move the lab due dates or take off the penalty. I don't want to move too many things like the labs, because what's going to happen?
Yeah, don't, because then it's piling up and I'm overwhelmed. So don't.
Exactly. And I was hesitant to move the exam, but I can't. I had to because we haven't covered it, and the lecture part is not on your time. So the lab part, it really requires more hours and to look at, normally you'll be in the lab from 8:30 to about 11. I believe the hours were on, if we were face to face. The lab starts at 8:30 in the morning, and then I believe it ends at 11:30. And you'll be, I would talk a little lecture about the lab and what you're doing. And here we don't have that luxury. I wish we did. So, yeah, the Victoria has a good point. The videos, you have videos, not only the ones we do here, but there are free videos already made from the topic, and sometimes that does help. Okay. Yeah, Dr. Kim, yeah, she put those together. And yeah, that is correct. That's her name, Dr. Kim Smith. She's the second lady in charge up there at GCC. Dr. Debbie is the boss up there. And she's the assistant chair. So just keep plugging away. And the best thing, like I said, is to send me an email, and I will get back to you ASAP as soon as I can get to it. Okay. And do not hesitate to send emails. Don't feel one of you wrote, I'm sorry to bother you. Don't think that way. That's my job. Okay. You are the customer. You're paying money for this. All right. So the way I took my education, I bother my instructors. At least I thought I bothered them as much as possible.
Hey, you had a GI Bill for like undergrad, okay?
Yeah, I
You were
did.
blessed.
But I pay for that.
For your doctorate. Yeah, you did pay for that. And thank you.
No, I paid for my GI Bill. I was sent to places I didn't want to go. Well, I guess I did.
Yeah.
You do pay for the GI Bill is not free. I know some people have
I
that.
know. I tell my husband that all the time. I'm like, but you have a GI. He's like, but I earned it.
Yeah. Well, I'm sure. Well, he's a veteran. What branch?
Yeah, he was in the Navy.
Navy. Okay. So was he on the ship?
Yeah, he's what do you call it? Like I don't know the exact name, but like dealing with like building the bomb